Okay, can you all see my screen? Can you also hear me well? Perfect. Okay, thank you very much to all the organizers for inviting me, and especially to Arina for reaching out. And yeah, the title of my talk is Skew Young Tableaux for Kazhdan-Lusztig polynomials of matroids. And I guess I'll just start. As Arina was saying, I'm gonna start by recalling some facts about matroid theory, since maybe not everyone knows about them. So if you know about matroids, this is just going to be an excuse to set notation. And then afterwards, I'm gonna introduce these polynomial invariants called Kazhdan-Lusztig polynomials. The definition of these polynomials, you'll see it can get very intricate. It's a recursive definition. Therefore, one of our goals was to find an operation on matroids that let us compute the coefficients in an easier way. So I will introduce the notion of stressed hyperplanes, and I will show how this let us solve some of the conjectures related to these polynomials. And then lastly, I'm going to interpret the coefficients of these polynomials using Skew Young Tableaux. And I'm also going to interpret our results in terms of the representation theory of a group of symmetry acting on the matroid. And everything I'm saying today comes from two different works. The first one is a joint work with Luis Ferroni, which is now at KTH, and George Nasr from University of Oregon. And the second work is joint with Trevor Karn from University of Michigan, George Nasr and Nicholas Proudfoot, also from the University of Oregon. Okay, so let's start by asking ourselves, what is a matroid? And to introduce matroid, I'm gonna start with something that I hope everyone is comfortable with, which is matrices and vectors from linear algebra. And I'm gonna fix a field K, and I'm gonna take a matrix, and I'm gonna state some obvious properties about columns in a matrix. The first one is that if I take an empty set of columns, this is a linearly independent set, so no relations because it's an empty set. The second property is that if I take an independent set of vectors and I remove some of the vectors, what I get is still independent. So removing things does not create new linear relations. And the third one is that if I start from an independent set of vectors and I keep adding vectors from my columns, choosing them from my column, I can always complete an independent set to a basis of the vector space. And I hope everyone agrees with these properties. And these will be the axioms that I'm going to use to introduce matroids. So matroids, what are matroids? They are a combinatorial abstraction of this notion of linear independence. So we think of vectors in vector spaces, and then we try to make this more general and only give a definition that is purely combinatorial. So a matroid is a pair E curly I. E is a finite set of size n, which we will call ground set. So a list of vectors, for example. And then curly I is a collection of sets that we call independent that satisfy these three properties. So the empty set is always independent. Then we have some monotonicity property. Every subset of an independent set is independent. And then a kind of, we call it augmentation property. So whenever I start with two independent sets and I know that one is bigger than the other, I can always find an element from the big one, add it to the smaller independent set, and I still get something that is independent. So now this is the definition of matroids, and I wanna find that the examples with lists of vectors as an example of matroids. So columns of matrices or vectors in a fixed vector space will be called K-realizable matroids. And then if a matroid is realizable over any field, it will be called regular matroid. And at this point, if you've never seen matroids in your life, you might ask, is it really necessary to give this new definition and just talk about vectors in vector spaces with this fancy new notation? And to convince you that introducing matroid is a nice thing to do, I'm gonna give you a second example of matroid. So now I'm gonna consider a graph. And in particular, I'm gonna consider the set of edges of a particular graph G. And I'm going to say that a subset of the edges is independent if it doesn't contain any cycle. And my claim is that this is a matroid, and that because it satisfies the 3 axioms for matroid. So of course, if I take no edges, there's no cycle in that. So the empty set is independent. Then if I start from a subgraph that doesn't contain any cycle, so a forest, and then I remove some edges, I cannot create new cycles. Therefore, the monotonicity property holds. And then lastly, we know we have some propositions that tell us that if we start from a forest, we can start adding edges until we reach a maximal point that is spanning trees. So graphs are also matroids. And if we look really closely at graphs and vector spaces, we will find out that there are many statements in these 2 seemingly completely unrelated theories that are actually the same statement. So for example, if we work in a finite dimensional vector space, we have a theorem that says that every basis is have the same cardinality. And then if we look at graph theory, we have a theorem that says that every spanning tree in a graph has the same cardinality. And the fact that these 2 statements look so similar comes from the fact that these are both matroids. So they are corollary of specific example that come from a specification of a general result in matroid theory. And at this point, if you've never encountered matroids in your life, you might think, okay, you gave me vectors and you gave me graphs. Is it still really necessary to talk about this stuff in terms of matroid theory? So whenever I give a talk on matroids, I always like to include the next theorem by Nelson that states that 0% of matroids come from either of these 2 classes. So this means that if I fix the size of the ground set, and then I pick at random a matroid with ground set of that size, I have a certain probability of picking a matroid that is realizable. And as the size of the ground set approaches infinity, this probability goes to 0. So asymptotically, no matroid looks like vectors from vector spaces. So it's a really nice motivating example, but now we know that this theory has dignity on its own. So there's a lot of stuff to uncover after looking at these 2 examples. So I hope that I convinced you that it's worth looking at matroids. So let me fix some terminology so we can talk about them. I call a maximal independent set a basis, and this of course comes from linear algebra. Then a set that is not independent will be called dependent. And then a minimally dependent set is called circuit. And this term circuit comes from graph theory. In fact, a matroid coming from a graph, circuits coincide with the cycles of the graph. And then lastly, we have a rank function. And this is exactly the rank for realizable matroids. This is exactly the rank function from linear algebra. So it is the maximal independent subsets that we can find, the size of the maximal independent subset that we can find. Okay. So now we can give some examples of matroids. We have the first one and the easiest one that will also be a sort of recurring example in this talk is the uniform matroid. It has 2 parameters. So K, we fix the dimension of a vector space K, and then we take n vectors in this vector space in the most general position possible. That is, in matroidal terms, that every K subset is a basis. So for example, the uniform matroid U23, to realize it, I'm gonna take a 2-dimensional vector space, which is a plane. And then I'm gonna take 3 vectors in the plane such that every pair is a basis of the vector space. So this red one here is a realization of this uniform matroid. And then a second example is a particular case of uniform matroids where when K and N coincide, and we call this particular uniform matroid a Boolean matroid. So now we want n-dimensional vector space, and we want n vectors that form a basis of this vector space. So for example, B3 is given by any triple of vectors, any set of 3 vectors in a vector space that form the basis of the vector space. Okay, I need one last definition from matroid theory, which is what is a flat. A flat is a set closed under rank, which means that every time I try to add an element that was outside the flat, the rank increases. And so we have a rank function. We can compute it on the matroid, and then we can find the family of all flats, and we can order the inclusion. And then we have a remarkable theorem, in my opinion, that states that this poset that we are forming is actually a lattice. I'm going to denote it curly L and call it the lattice of flats of the matroid. So for example, we can take these 5 vectors in a 3-dimensional space, and let's see what the lattice of flats look like for this example. So in realizable matroids, flats are easy to determine because they are in bijection with all the possible subspaces that we can span with the different vectors. So for example, if I take no vector, the span of this set is going to be just the, which is a 0-dimensional vector space, subspace. And that's why I put it here in the rank 0 of my lattice. Then if I look at 1-dimensional vector spaces, every vector here spans a line. And that's why I get these 5 rank 1 flats inside the lattice of flats. Now for dimension 2, something more interesting happens. Because for example, now if I take V1 and V3, these 2 vectors span this light orange plane. But if I now add V2 to my set of vectors, they still span the same subspace. So V1, V3 is not a flat, because if I add V2, the rank does not increase. But 1, 2, 3 is a flat, and that's why I put it here in my rank 2 flats. And the same goes for 3, 4, 5, which span this gray gray plane here. And all the other ones are all the possible planes that I can span. For example, V1, V5 spans this one, etc. And then lastly, we always have the k-dimensional subspace. It's the whole space. And that's why we always get the whole ground set as a rank k flat. What does the lattice of flat look for uniform matroids? All the flats are all the possible subsets of size strictly less than the rank, and then again the whole ground set. Why is that? For example, if we take the uniform matroid U34, I need a 3-dimensional vector space, and I'm going to take 4 vectors in general positions. They span 4 different lines, and every pair spans a plane, but all the other vectors do not lie on that plane because I took them in general position. And that's why the lattice of flats of a uniform matroid looks like this. Okay, now we have a theorem that actually this lattice of flats of the matroid encodes all the properties of the matroid. So we can determine the matroid just by looking at the lattice of flats. And there is a theorem that tells us that there is a correspondence between matroids and geometric lattices. Geometric lattices are particular posets that satisfy certain properties. And this correspondence is given by, if I start with a matroid M, I'm going to take the lattice of flats, and this will be a geometric lattice. And then if I start from any geometric lattice, I can always construct a matroid from it such that its lattice of flats is isomorphic to the lattice I started with. So from now on, I'm going to talk about matroids, not using the independent sets, but I'm going to use this poset theoretic definition with the lattice of flats. Okay, we have a lot of operations on matroids that take in a matroid building a bigger or a smaller one. I'm going to give you just 2 examples because these are the ones that we need for our talk, for our purposes. The first one is the restriction, and I'm going to give you the definition only in the case we want to restrict to a flat F. I'm going to say that this operation gives you a new matroid that we call M upper F. And I claim that the lattice of flats of this matroid actually coincides with the interval that goes from the minimal element up until the flat I'm restricting to. So for example, if I want to restrict to the flat 1, 2, 3, which is this subgraph in this graph here, the statement is that if I want to build its lattice of flats, I can just look at the intervals in the lattice of flats here. So this will be the lattice of flats of the restriction. My second operation is the contraction by a flat. And again, I'm gonna build the matroid by stating what the lattice of flats will be like. The matroid will be denoted with M lower f, and its lattice of flats will be isomorphic to the interval that starts from f and goes up until the whole ground set, the maximal element. And we call it contraction because this is exactly the operation contraction on graphs. So for example, anytime I have a graph, I know that I can contract an edge, for example, the edge 1. So I can remove the edge and identify the two endpoints. What I obtain is a new graph, which is again a matroid. So the lattice of flats, and I state that the lattice of flats is exactly this interval over here. And with these two operations, we also know that we can also state this proposition that every interval in a matroid is a matroid, meaning that if I start from any geometric lattice, I can take an interval, and what I obtain is a new geometric lattice. Because if I take the interval fg inside the lattice of flats, this corresponds to a new matroid where I contracted something and restricted to something else. Okay. A nice thing we can do on every poset, and we want to do it in the lattice of flats as well, is computing the characteristic polynomial. So we can do this recursively using the Mobius function mu of the poset. I think everyone knows how to do it, but here's an example anyway. The computations goes recursively. We start from the minimal element and we give it the value 1. And then for every other element in the poset, we look at everything that is below it, add up all the values that we already gave to them, change the sign, and this is the value that we're going to give to that element. So for example, if I look at the rank 1 flat 1, the only thing that is below it is the empty flat. It had value 1, so we change the sign to a -1, and that's the value that we give it to him. And the same goes for all the other rank 1 flats. Now, if I look at the element 1, 2, 3, the things that are below it are 1, 2, 3, and the empty set. I sum all these values. This is a -1, -1, -1, +1. So it's a -2. I change the sign to a +2, and this is the value that I give to this flat. And the same goes for 3, 4, 5. While, for example, if I look at 1, 4, I only have 1 and 4 and the empty set below it. So it's a -2 +1. It's a -1, change the sign to a +1, and that's the value I give to it and all the other rank 2 flats here. And then I add up all these values, I get a +4, I change the sign to a -4, and this is the value I give to the whole ground set. Now to compute the characteristic polynomial, we just take all the values on the same row, add them up. I get a 1, -5, +8, and -4, and these are exactly the coefficients that I give to a polynomial, and I read them from bottom to the top, and this will be called the characteristic polynomial of the matroid. Okay, so this was the recap on matroid theory, and I always forget to ask if there are any questions, so I put some extra slide in here to remember. So does anyone have any questions on what matroids are? If not, we can go on with defining what Kazhdan-Lusztig polynomials are. So Kazhdan-Lusztig polynomials are 3 polynomial invariants that can be defined using a specific recursion on the lattice of flats of the matroid. And we are interested in computing them because it turns out that they have both combinatorial and geometric properties that are very interesting. So they encode something meaningful about the matroid. So that's why they're worth looking at. And the 3 polynomials are these ones: the polynomial P, called Kazhdan-Lusztig polynomial, the polynomial Q, called inverse Kazhdan-Lusztig polynomial, and the polynomial zeta, which is the zeta polynomial of the matroid. The definition is given for P by Elias, Proudfoot, and Wakefield in 2016. For zeta is given by Proudfoot, Xu, and Yang in 2019. And for Q, it's given by Gao and Xie in 2021. And the definition goes as follows. We have some base case. So when the rank of the matroid is 0, the values for P and Q are either 0 or 1, depending on the fact that the ground set is empty or not. And then we go with a recursion. So the definition for P tells us that we look at all the elements in the lattice of flats. We compute some of the characteristic polynomial for every contraction and the Kazhdan-Lusztig polynomial for all the restrictions. We do this product, we add them up, and what we get is the Kazhdan-Lusztig polynomial of the whole matroid with flipped coefficients. And as you can understand, this computation becomes very daunting as the lattice of flats increases in size. This recursion here doesn't identify the polynomial. However, if we fix this extra condition on the degree, which is the degree of the polynomial is strictly less than the half of the rank of the matroid, the polynomial is defined uniquely. And we also have a recursive definition for the polynomial Q. And then zeta is just a sum over all the possible contraction and the Kazhdan-Lusztig polynomial of all the possible contraction shifted by the rank of the flat we are contracting by. And if any of you is interested in posets, they might recognize this product here as convolution products inside the incidence algebra. So since we are combinatorialists here, I want to try to give an equivalent definition just by looking at the incidence algebra of the poset. So if you don't like incidence algebra, you can turn your brain off for this slide and we'll catch you up later in the next slide. So if I have a poset P, I can look at the incidence algebra. It's the algebra of all the functions that take intervals in the poset and associate to them a certain polynomial. We have a convolution product denoted with star and an identity element for this product denoted delta. If the poset is ranked, we can define an involution, which is flipping the coefficients as before. And now I want to look at some interesting functions inside the incidence algebra called P-kernel. So a function kappa is a P-kernel if it is invertible. And the inverse of the function is exactly kappa bar, where bar is the involution that we defined before. And the characteristic polynomial of any poset can be proved to be a P-kernel, the characteristic polynomial being K. And we have a theorem by Stanley that tells us that when we look at the incidence algebra and we find a P-kernel, the following things are univocally determined. So we define the right Kazhdan-Lusztig function by being the function that when convoluted to the right of the P-kernel becomes the involution of itself. And then if you look at what we had before, it's exactly what's happening here. We're convoluting chi with P and we get P with flipped coefficients. And then we also have a notion of left Kazhdan-Lusztig function, which we don't need for the rest of the talk. But since we know what the we might know what the Möbius function is, it's worth to point out that the inverse of the Möbius function is the left Kazhdan-Lusztig function. P is invertible, and the inverse is the function Q. And that's why the name for Q is inverse Kazhdan-Lusztig polynomial of the matroid. And this means that up to a certain sign, when we convolute P with Q, we get the identity function delta. And then lastly, the zeta function is defined using the left and right Kazhdan-Lusztig function in this way. And I wanted to include this poset theoretic definition because you might have already heard about Kazhdan-Lusztig polynomials, but in a completely different setting, which is Coxeter groups and the Bruhat order. And this is not a coincidence. Actually, this theorem here is a generalization of those Kazhdan-Lusztig polynomials due to Stanley and Brenty that were able to generalize the notion of Kazhdan-Lusztig polynomial from the Bruhat order to any weakly ranked poset. And that's why our polynomials now have this name. So again, I wanna stress the fact that using this definition doesn't let you go very far with computations. Even if we plug this in a computer, this becomes very daunting because the size of the lattice of flats becomes very large very quickly. And then this polynomial here needs to be computed recursively with the Möbius function, and this polynomial here is also computed recursively using the characteristic polynomial. And therefore, not much can be seen starting just with the just looking at the definition. But for example, we are lucky. We said that uniform matroids are the easy matroids that you want to be friends with. And lucky for us, we already have a closed formula for uniform matroids. But as you can see, even for the easy matroids, uniform matroids, the coefficients of the polynomials become very ugly very quickly. So you can imagine with the generic matroid how things can go bad very quickly. It's also worth to state a very interesting theorem that was proved last year, even if the paper is not already published. So maybe we need a plus here because we don't know when it will be published. And the theorems are the following. The Kazhdan-Lusztig polynomial is actually a polynomial with non-negative integer coefficients. And this is due to Elias, Proudfoot, and Wakefield in the realizable case, and to Braden, Ha, Mather, Proudfoot, and Wang for the general case. And we also know that the zeta polynomial has non-negative integers and its coefficients are unimodal. This is due again to Ha and Wang in 2017 for the realizable case, and from this same set of authors for the general case. Why do I want to talk about this? Because these theorems were proved geometrically. So the proof was first given for realizable matroids by building specific varieties associated to the matroid, and then computing the intersection cohomology for these varieties, and then interpreting these coefficients as Hilbert's series for those intersection cohomology. And then when in the general case, we don't have geometry associated to our matroids because we don't see them as lists of vectors. So what they do is they build an intersection cohomology module, IH of M, that looks like the intersection cohomology module for a variety, even if the variety is not there. And then they prove that some results, some Hodge theoretic results hold for this module. So for example, the fact that the zeta polynomial has unimodal coefficients is a consequence of the fact that in IH of M, we have Poincaré duality and the Hart-Lefschetz theorem holds. It's still important that we were able to prove these results, even if it was with metric or algebra geometric inspired proof, because that let this set of authors solve a conjecture that has been open for decades called top-heavy conjecture. And the conjecture was again on the lattice of flats of the matroid. And it stated that the number of flats in rank J is always less than or equal to the number of flats in co-rank J. So the top half of our lattice of flats always have more stuff. And yeah, again, this conjecture is completely combinatorial. It only needs a poset, but the only way that we've been able to prove it so far is going through this geometric interpretation for the matroids. So the problem maybe is if we only want to look at combinatorics, again, this formula doesn't tell us much about the polynomials. So maybe that's why we needed to completely change the way we saw we looked at the problem, and then geometry came to help and helped us solve those conjectures. But again, some combinatorial conjectures are still open for these polynomials. So there is still a lot to do for these invariants. And here are some examples of open problems. The first one concerns the roots of the polynomials P and zeta. So that we have a conjecture of real rootedness. Then, if you remember, I told you that the degree of the polynomial had a certain maximal bound, half the rank of the matroid. But this formula is so bad that we still don't even know when the degree of the polynomial is exactly the maximal possible value. So we have some conditions on the matroid that are conjectured to give us the maximal possible degree for the invariant. And then we talked about the uniform matroid and its Kazhdan-Lusztig polynomials. And we have a conjecture stating that when you fix the rank and the size of the matroid, this polynomial has the biggest coefficients possible. And then I want to include in this list of open problems, since we like combinatorics, I'm still looking for a completely combinatorial proof, so not inspired by algebraic geometry of the fact that these polynomials have non-negative coefficients. So I hope I convince you that these polynomials are interesting. They helped us solve some conjectures, and there's still a lot to do. So they're still interesting. It's still nice to work on them. So are there any questions on the definition of these invariants? Okay, then we'll move on to the third part, to the third bullet point in my list, which is the operation of stressed hyperplane relaxation. And okay, so what is the goal now? We want to find an operation that lets us transform a matroid in another matroid such that the Kazhdan-Lusztig polynomials are changed in a controlled way. So we want something that is well behaved with respect to these invariants. And luckily for us, we were able to find it. And to describe this operation, I'm going to give you a definition. So this is due to Luis, George, and I. We define a stressed hyperplane in a matroid to be a flat of co-rank 1. And it is such that the restriction to this flat is a uniform matroid. So for example, if we look at the lattice of flats that we had from the beginning, and we look at this particular flat here, it's in co-rank 1. And then yes, okay. If I look at the restriction to it, this looks like a uniform matroid. So this will be a stressed hyperplane. And I want to mention that this definition is new, but it's also a generalization of something that was already known in the literature. So in the case where the size of the hyperplane is exactly the rank of the matroid, these were known to be, and these were called circuit hyperplanes. So this notion of stressed hyperplane is a generalization of circuit hyperplanes. Okay, what can we do with stressed hyperplanes? We can relax them. And by that, I mean that every time I start with a matroid and I find a stressed hyperplane in the lattice of flats, I can build a new lattice of flats from it by removing the hyperplane and replacing it with a bunch of new flats. And the theorem tells us that what we get is again a geometric lattice. So it's again a matroid, and we call it relaxation of the matroid M. So we have our example here. We already found out that this is a stressed hyperplane. So I want to apply this operation, and what I get after performing one relaxation is this new lattice of flats where I replaced it with these 3 new flats. And then again, I find a different stressed hyperplane in what I'm left with, so I can perform my relaxation again. So I can remove this flat and I can replace it with a bunch of new flats here. And lucky for us, in this case, we obtained a very easy geometric lattice, and a very easy lattice of flats. It is the lattice of flats of a uniform matroid, which, as I hope like if you get something from this talk, is uniform matroids are your friends. So whenever you find uniform matroids, you are very happy. So after 2 relaxations, we made our lattice of flats very easy to work with. So now the question is it good for Kazhdan-Lusztig polynomials? And the answer is yes, thankfully. So how are the Kazhdan-Lusztig polynomials changed under relaxation? Our theorem, we prove a theorem that tells us that if I want to compute the Kazhdan-Lusztig polynomial of the relaxation, I can start with the Kazhdan-Lusztig polynomial of the original matroid, and then I need to add a polynomial, a correction term that is a polynomial. And the remarkable thing is that it does not depend on the matroid M, but only on the rank of the matroid and then the size H of the stressed hyperplane I relaxed. So in a sense, these correction terms can be put in a table, and then every time I find stressed hyperplane in my matroid, I can relax it, and I know exactly from my table by how much the Kazhdan-Lusztig polynomial is changed. And the same goes for Q and for zeta as well. So I just didn't want to put the same statement 3 times. So great. So this maybe will let us solve some of the conjectures. There are 2 classes of matroids that are called sparse paving and paving. And sparse paving is actually a subclass of the paving matroids. These classes were already known in the literature again. I'm not going to give you the definition that they were defined with first, but I'm gonna state what they are in terms of relaxation. So for us, a paving matroid is a matroid that can be relaxed to a uniform matroid. This is great. Why do we care about sparse paving and paving matroids? Because we have a conjecture that tells us that 100% of the matroids are sparse paving. And again, by that we mean that asymptotically, as the ground set of the matroids grows to infinity, the chance of picking a matroid at random and it being a sparse paving approaches 1. So whenever we find a result for sparse paving or paving matroid, we're actually finding a result that probably will be true for almost every matroid. Why is it a good news for us? Because this relaxation operation tells us that we are able to find a closed formula for almost every matroid. Why is that? Because how can we compute the Kazhdan-Lusztig polynomial of a paving matroid? We know that after relaxing everything, we go up to the uniform matroid. We have a closed formula for that. And then we just need to keep track by how many correction terms we added to get to the uniform matroid. So we just need to subtract from this a bunch of correction terms. So this indeed is a closed formula for all paving matroids. And now you might argue, okay, this is a closed formula if you're able to give me a closed formula for this correction term, because otherwise, if I have a recursive formula for it, I just shifted the problem 1 step after. So can we find a closed formula for this matroid, for this correction term? And the answer is yes. Because since these correction terms are proved to not depend on the matroid, we can compute them using easy matroids. So for example, we show in our paper that these correction terms are actually a difference of Kazhdan-Lusztig polynomials of uniform matroids, for which we have a closed formula. So indeed, the formula from before is exactly is indeed a closed formula. Now, to give an answer to all those open problems, I would like for these polynomials to be non-negative. And for us combinatorics inclined, what is the best way of showing that an integer is non-negative? We want to prove that it's counting some stuff. So with this cliffhanger in the middle of the talk, I'm going to ask if there are any questions on the operational stress hyperplane relaxation.
I have a stupid question maybe, but what's the difference between sparse paving and paving?
Oh, yes, thank you. So sparse paving are a subclass of paving matroids. Paving matroids are the ones where I have only stressed hyperplanes. In sparse paving matroids, I only have circuit hyperplanes. So in here I have stressed hyperplanes. In here I have circuit hyperplanes. So it's a subclass of paving matroids where circuit hyperplanes were a special case of stressed hyperplanes. And if you know a bit more about matroids, being sparse paving means that you are paving and your dual is also paving. So this is how sparse paving matroids are defined. Thank you. Any other question? Okay, so let's introduce the Skew tableaux. I think everyone knows what these diagrams represent, but just to set the notation, I can start with a partition of an integer n, which is a non-increasing positive sequence such that its components sum up to n, and to any of these partitions, we can associate a diagram that looks like this. So we have some boxes, and the number of boxes are exactly given by our partition. So for example, for n equal 15, this is 8, 5, 1, 1. So I have 8 boxes, 5, 1, and 1. And an interesting thing we can do with these diagrams is we can try to fill the diagram using all the numbers from 1 to n in such a way that all the rows and all the columns are strictly increasing. And any of these fillings is called a standard Young tableau. A second thing we can do with Young tableaus is we can take a partition of n plus m, a partition of m, and then if the diagrams satisfy some nice properties, we can define a skew diagram that looks like this. So what did we do? We took the diagram for lambda. It was the big one here. Then we took the diagram for mu. We make the coincide the upper left corner here. And we removed all the boxes that were inside of mu. And what we're left here is a new different grid with n boxes, because I started with n plus m boxes and I removed m of them. And then I can still ask in how many ways I can fill this diagram in with numbers from 1 to n in such a way that the rows and the columns are strictly increasing. And this will be a skew Young tableau, a skew standard Young tableau. For our purposes, we need 2 particular shapes of diagrams. We have a standard Young tableau that depends on 3 parameters, a, I, and b, that looks like this. And then we have a skew Young tableau that also depends on 3 parameters, a, I, and b, that looks like this. So we started from this big diagram, and then we removed the rectangle from it. And then I'm gonna use the following notation: lowercase site AIB, lowercase skite AIB counts the number of standard Young tableaus and skew standard Young tableaus that fill these shapes. We are interested in these shapes because there is a result by Lee, Nasr, and Radcliffe that interprets the coefficients of the Kazhdan-Lusztig polynomial of the uniform matroid by counting the filling of some particular skite shapes. So we plug these values in the 3 parameters, we count the skew standard Young tableaus, and these are exactly the coefficients of the Kazhdan-Lusztig polynomial. And in our paper, we do the same thing for Q. So we interpret the coefficients by counting the filling of that standard Young tableau, a standard Young diagram, by plugging these values inside the 3 parameters that define the shape. We need this because as a consequence of this fact, we are able to actually produce another closed formula for the correction terms, P, Q, and zeta. And we do so by counting the fillings of a slightly different shape. We call it skite bar. And the only thing that changed is the fact that we removed this box in the upper left corner. But the fillings of this skew diagram are exactly the coefficients of the correction terms. So as a consequence, we have the non-negativity of the coefficients. We're counting something. And then we also know at what point we need to stop. So we know that after I be equal k minus 1 half, we know that we have 0 legal fillings. And so we also know that the degree of this polynomial is exactly what we want. This is great because now we can take our formula for all paving matroids back. And then now that we have the non-negativity of the coefficients of these polynomials and we know the degree of this polynomial, we can give an answer to all those open problems that I showed you before. So after using a lemma that gives us a bound on what the number of possible circuit hyperplanes is in sparse paving matroids, here are a list of the answers that we give in two different papers. So firstly, this formula here now is not recursive. So computers like it very much. So the first thing that we were able to do is we gave a formula for the Kazhdan-Lusztig polynomial for all sparse paving matroids with at most 30 elements. This is in the order of tens of thousands of matroids, and all of them had real roots. So this is huge evidence supporting the conjecture of real rootedness. And then from this formula here, thanks to this bound, we were able to prove combinatorially that all sparse paving matroids have no negative coefficients, because we start from some known coefficients and then we remove something that is not too big. And then again, this also let us give our results on paving matroids regarding the degree of these Kazhdan-Lusztig polynomials. And then lastly, from this formula, it's pretty evident that Kazhdan-Lusztig polynomial for uniform matroids are the ones with the biggest possible coefficients in the class of sparse paving matroids, because we start from something and then we remove something positive. So actually for all the other matroids, the coefficients will be lower. That's great. We found some answer for almost every matroid, if that conjecture is true. Now the question you might ask is, how come we found those weird shapes? Like, how is it possible that those shapes actually count what the coefficients are? So why do we get these Q diagrams? So for us, it was kind of by chance, but lucky for you, now we have a more deep answer. So this is actually a consequence of some representation theory of the automorphism group of the matroid. So let me give you some definitions before I can convince you that this was not by chance. This was going to happen. So let's go back to this really important result. The Kazhdan-Lusztig polynomial has integer non-negative coefficients. So what do I want to do when I look at natural numbers? One thing I can try to do is build what are called equivariant polynomials. And by that, I mean that I want to take this and I want to upgrade everything to a higher categorical level. I'm going to be very informal. So what happens? I want to find some vector spaces that are in some way canonically associated to our object, in this case, a matroid, and then such that the dimension of these vector spaces are these coefficients. And then whenever I have an action of some group of symmetries on these objects, I want to study what the action of this group of symmetries is on these vector spaces that I'm trying to define. So roughly the idea goes like this. Whenever I have a natural number, I want to replace it with a representation of the finite group that is acting on my object. If I start with an integer coefficient, I cannot ask for it to be a representation of the group. So I need to work with what are called virtual representations. If you know what a Grothendieck group is, the ring of virtual representations is the Grothendieck group of the representations. And by that, we mean that in this ring, we make sense of a writing that looks like this. So not only we can take direct sums of representation, now we can take formal differences. So a representation minus another representation. And then if I have a polynomial, I want to replace this with a graded virtual representation. So it's a polynomial in the variable t. And in every coefficient, I don't have a number now. I have a representation of my group that is acting on my matroid. So what is the goal now? If we have a group of symmetries acting on the matroid, we want to find these equivariant polynomials, so these graded virtual representations, such that now if I look at the coefficients, so a virtual representation in my new categorical invariant, its dimension is exactly the coefficient that I had in the non-equivariant setting. And we want to do this for P, Q, and zeta. Lucky for you and us, we already have a nice formula for all the three invariants. This is due to Gideon, Proudfoot, and Young for P, Proudfoot, Xu, and Young for zeta, and Proudfoot for Q. And again, this formula now is again recursive. We have some base case if the rank is 0. It's either 0 or the trivial representation, which has dimension 1. And then we again have a recursive definition but now you can see that we have something like inducing representations or taking tensor products, because we're not working with numbers anymore, but with representations of a group. Okay, uniform matroids are our friends, so we hope that there is a closed formula for uniform matroids. Uniform matroids have a very standard action of the symmetric group Sn. It's just a permutation of all the elements of the ground set. And we have a theorem by Gauxau and Young from last year, 2021, that tells us exactly what the coefficients are for the equivariant Kazhdan-Lusztig polynomial. These representations look like this. And what do I mean by V lambda minus mu? There are some statements in representation theory that tells us that every time we have a skew diagram, so something that looks like this, we can find univocally as a representation of the group that is described exactly by the skew shape. And this representation is called the skew spec module. So if you know nothing about skew spec module, you just need to know that this little drawing here gives us exactly what the coefficients are in this categorical setting. So we know what the representations are for the uniform matroid. But we already found some skew diagrams before in this talk. So is this a coincidence? Because if we look at this skew spec module, which is indexed by this skew diagram, this looks really similar to the skew diagram that we're counting the coefficients in the non-equivariant setting. And this is not a case, because this diagram and this diagram are actually the conjugate of one another. And by conjugate, I mean I can reflect the diagram along the diagonal. And then we have some theorems from representation theory that tells us that counting the filling of this tableau actually tells us the dimension of this representation. So this diagram had to be that one, had to be the one that counted the coefficients in the non-equivariant case, because those coefficients needed to be the dimension of these coefficients in the equivariant case. So what happens for the relaxation? So in the second work I was referring to, the one with Trevor, George, and Nick, we find out that actually the relaxation works well in the equivariant case as well. So again, we can start with an equivariant Kazhdan-Lusztig polynomial. We can perform a relaxation. And now the difference between these two polynomials is a correction term that does not depend on the matroid, but only on the rank and the size of the stressed hyperplane. And so this correction term has as coefficients isomorphism classes of some representations that are known. So they do not depend on the matroid. And we were also able to compute them. So what are these representations? Again, these representations are indexed by some particular skew diagrams. And as you might expect now, the skew spec modules associated to these coefficients are actually very close to the skew diagrams that counted the coefficients in the non-equivariant case. And once again, the number of fillings of these shapes is exactly the dimension of this skew spec module. So what is the conclusion now? I hope I convinced you in this hour that Kazhdan-Lusztig polynomials are very important invariants. They give us something interesting both for the geometry and the combinatorics of the matroid. The operation of relaxation was particularly nice for us because it helped us conclude a lot of stuff for many matroids without going through the recursive definition. And this operation was also nice because it still held in the equivariant setting, so in something that was even more general. And it also told us something about what the group of symmetries is in our matroids. And then this gives us hope because there were some theorems that were only proved geometrically, but in this case, we were able to find some combinatorial way. But anyway, this combinatorial way was actually the shadow of some representation theoretic results. So we proved them only with combinatorics, but then we understood that they were a consequence of something deeper from algebra. And with this, I thank you very much for your attention.
Okay, thank you very much for the very good talk. So I think we should thank the speaker. Yeah, thank you very much. So now if there are any questions from the audience, feel free to ask them. Okay, then I guess I will stop the recording.